The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and welcome to the webinar titled Analysis Using Fuel Cell Material Handling Equipment for Shaving Peak Building Energy. My name is Chris Worth, and I am the organizer for this meeting. We'll begin shortly, but first I have a few housekeeping items to tell you about. Today's webinar is being recorded, and the recording, along with the slides, will be posted to our website in about 10 days. We will send out an email to attendees once those are posted to the site. All attendees will be on mute throughout the webinar, so please submit your questions via the questions box that you should see on your webinar panel. We will cover those questions during the Q&A at the end of the presentation. With that, I would like to introduce our DOE host, Pete Devlin, joining us from the Department of Energy headquarters in Washington, D.C. Pete is a market transformation project manager in the Fuel Cell Technologies office. Good afternoon, Pete.
All right, thanks, Chris. Thanks, everybody, for joining in. I'd like to say a couple things about why we're doing this analysis and how it might benefit various groups, customers, industry people, and so forth. We started a material handling deployment project back in 2009, and we funded 400 pieces of equipment in various parts of the country with various industry partners. That turned out to be extremely successful. You can read about the business case on the National Renewable Energy Lab website. The business case was limited to the productivity and a few other ancillary issues that enabled fuel cells to compete and actually showed a better prospect than electric battery lift trucks. And as a result of that, there's now over 8,000 additional units in the field in the U.S. With no DOE help at all. So that 50-50 cost share through the Recovery Act was extremely successful. So with that as background, today we'd like to hear about using material handling equipment for peak shaving and building power as yet another, another business prospect to even increase the economic advantage of material handling equipment powered by fuel cells. I'm going to turn it over to our presenter, Michael Penna. Michael's a longtime analyst at National Renewable Energy Lab. He holds several engineering degrees, mechanical and chemical. Has an MBA. He's worked in industry at Plug Power before he came to NRELM. And Mike has been looking at how can a fuel cell material handling equipment or a fleet of them in in a building actually help with the rates that you would experience during peak hours in some parts of the country. So with that, I'll turn it over to Mike.
Thanks, Pete. Again, to reiterate, what we're looking at is supporting building energy demands with material handling equipment. What we have in this slide here is a picture of what the energy demand might look like for a building from over time. And as you can see, it's not evenly distributed over time. Sometimes there is what's called peaks in the demand, and this causes a great deal of challenges for the grids. They have to basically have equipment sitting on the side ready to turn on, or they have equipment that's not being utilized at full power, ready to increase in power so that they can supply this power to buildings. So what we're looking at is on the demand side of the grid, is there a way to decrease those the peaks and subsequently not being charged as much by the utility for having those peaks demanded from the grid. And basically, we have electricity is normally delivered by the grid to the building. We would connect 1, 2, or more electric forklifts, or rather hydrogen forklifts, into a DC bus and provide offset some of the power demands from the grid through an inverter. We focused on a favorable market namely in California. We looked at PG&E rate structure, and specifically for smaller users, the utility provides flat electricity pricing. So basically per kilowatt hour of energy usage, they get charged. However, as user becomes larger and larger, or as you encounter larger users, their peak demands start affecting the grid, and the utility wants to minimize the peaks and pass any expenses to the final user. So as you can see here, for smaller users, there are no demand charges, but as the user becomes larger, we have demand charges for 3 different rates plus standby charges. We explicitly focus on the E19 time of use schedule, and as you can see, we have energy expenses for the final user, and also we have summer demand charges and also winter demand charges. There are actually 3 tiers depending on if the user has any of their transformers, or are they receiving final voltage to the facility. We're going to, within the analysis, look at no transformers being owned by the facility, and basically looking at secondary schedule. All the analysis is performed in great detail, great rigor. We have benchmarked our accounting versus actual bills from customers, and we're able to match the utility expense down to the last penny. We do, for every analysis, we do an analysis before consideration of any peak shaving equipment, as well as after any peak shaving has been simulated for a building. And we look at the difference in the billing to the end customer. We look at are they paying more, are they paying less, and we quantify those expenses. On the equipment, material handling equipment, we depreciate the power generation equipment only, since we're only using, we would be only using the fuel cell in a park mode. We will not be using any of the moving machinery of the forklift. So we're only depreciating the power generation, and we're depreciating it on an hourly basis. However many hours we operate the equipment, we assume that it has a life of 10,000 hours, which was benchmarked by industry reviewers. And also we're looking at an efficiency of 13 kilowatt hours that a fuel cell can produce for every kilogram of hydrogen that it consumes. Any power electronics, inverters, we're assuming that they have no maintenance expense. They don't have significant moving parts. The maintenance is essentially trivial. This slide goes a bit more into the details. We've simulated a total of 103 actual measured commercial loads in California. 99 are based off of an anonymous database for commercial loads, but we also have some facilities that we know that they have material handling equipment in them, and we have a little bit more details. As far as specifics, we've done the analysis with sensitivity behind it, and in green here we display the baseline analysis, and in black numbers we show all the sensitivity values that we have covered. So, for example, we're looking at the material handling equipment with 8 kilowatts nominal being available for power takeouts. We use 90% of the power. This has to do with potentially the equipment might not be able to produce the full power if it's not moving. We gave it a bit of a distance for inverter or any other power electronics. 100, 0 assumes that you have on-site inverters on board hydrogen. We sweep that from 0.7 to 3 kilograms, but we also include a possibility of the fuel cell being refueled. So this have available hydrogen. For the actual peak shaving, %, peak shaving up to 20%. Once you get beyond 20%, you're this is before any taxation. We're looking. So what does this look like? This chart is a little bit of an eyeful. It's one of the facilities in a color representation of its electric demand. On the x-axis, on the horizontal axis, we have time of year. On the y-axis, we have time of day. So what we're looking at, each of these stripes basically represents a day of operation. When the color is darker, the facility is using less power. As the facility uses more power, we're seeing the color turn a little bit brighter. We have the same data represented here on a time basis, basically time on the x-axis and electricity consumption on the y-axis. And I'm going to click through and demonstrate how the peak shaving works. So if we select 1% peak shaving, on this chart here, we'll see when a fuel cell would actuate and produce some power to shave off those peaks. And on this axis, you'll see how the red portions are the ones that are being shaved off. What we're going to see on this table here in green is energy savings, or rather expense savings. And in red, we're going to see costs that are incurred by the facility. At 1% shaving, we're looking at all-in IRR or 43%. This is 2% of peak shaving. We can see that we're hydrogen. We're also using more depreciation of the forklift. We're still doing well. We're savings are outpacing any of the expenses. And as you can see, as we click through, generally the pattern is that you're shaving deeper into the profile, and in order to subtract a certain percentage of the overall expense, you end up spending more time of operating the fuel cell. And at the end of the day, you get to a point where expenses start to exceed your savings. So there is an optimum there of how much you want to peak shave, and typically less is more. The more efficient your return on investment is going to be, the less you shave, but you still benefit from that application. And we can see all the way out to 15%. At 15%, you're using so much fuel, and you're depreciating any plugged-in equipment that it's basically not worth doing. But there is a happy medium. I'm going to run through a quick example just with a little bit more detail. I'm picking out the head profile that has 300 kilowatts base demand, and the annual peak is 424 kilowatts. If we're looking to shave 2% of the peak demand, we will need about 8.5 kilowatts of forklifts. We said that we're using an 8 kilowatt forklift as a baseline, so with 2 of them, we will be able to supply 8.5 kilowatts. Maximum hydrogen available is a kilogram, so we'll have 2 kilograms available for a total of 26 kilowatt hours a day of power, of energy that we can produce for the offsetting grid purchases. Interconnect capital cost, we're looking at $2,500 for power electronics and $2,000 for the installation of the equipment, for a total of $4,500 for the project. When we run an analysis of peak shaving for the hourly analysis, it's actually a 15-minute analysis, we're estimating 190 kilowatt hours of energy provided throughout the year, and a total of 53 hours of operation. And throughout the year, we will be consuming just shy of 15 kilograms of hydrogen. This analysis, you don't need to really see the numbers here, but basically we're looking at analyzing the grid's expenditure without peak shaving, and also we do a detailed analysis with the peak shaving in order to arrive at these set of numbers. So we're looking at 360,000 of baseline expenditure for the grids without peak shaving, and once we put peak shaving on, we get up to we shave about $2,000 of grid expenditure. This is an example of the cash flow analysis. Again, it's just a simple project level analysis. We have our expenditure at year 0, or basically the beginning of the first analysis year, and then at December 31st of each of the performance years, we're looking at the net of revenue minus expenditure, and based off of that, we calculate a net present value given the 10% discount rate, as well as internal rate of return. In this case, it comes out to 41%. Depending on the size of the business that's operating this, the NPV is not an astronomical number, but every bit helps. If we want to consider a little more detailed sensitivity of performance, what we can look at is, well, what if we shave a little bit less or a little bit more? On the x-axis of this diagram, we're looking at depth of peak shaving, and in blue, the big blue line, we have internal rate of return calculation. The orange line is net present value, and in dotted lines, we have number of forklifts. So anywhere from 0 to almost 2%, we only need 1 forklift, and anything, even increments, in order to shave deeper, we need to add a second forklift, third, fourth forklift. As we can see, there is a benefit we get up to in excess of 48% IRR, but once we add a second forklift, that yields additional capital expenditure, and the IRR drops correspondingly. Depending on what a business is interested in, if strictly IRR is the metric or some mix of IRR and net present value, arguably in this case you might want to shave somewhere closer to 2.5%. But that depends on the business objective. Now, an important question here is what happens if you refuel the forklifts? Does that help you? So let's say that we have a forklift, and instead of being limited to 1 kilogram of hydrogen per forklift, let's say that it can operate a longer time throughout the day. The second set of slightly grayed out numbers that come up is the performance. They reflect the performance that you obtain if you were to refuel the forklift throughout the day. So basically, as it gets depleted on a busy day, when electrically busy day, you would have somebody either come refuel it, or the forklift would be perpetually connected to hydrogen. And you can see that since we're operating the equipment more, we can get to larger net present values and also achieve higher internal rates of return. In this diagram, we show a sensitivity of that particular scenario that we were examining, and we've looked at what happens if you have larger forklifts or smaller forklifts. What happens to the internal rate of return, which is the lines in black, and those are really the ones that we want to look at. So at the baseline, we had 41% IRR. If we look at larger forklifts, we obviously wouldn't need 2 of them. We would need only 1 for 2% peak shaving, and we get a little bit better internal rate of return. It's a larger fuel cell, but it ends up being a better choice for peak shaving applications for this particular scenario. When we look at power electronics costs, it is very important to, it is very beneficial if there is equipment that we don't have to purchase and attribute to the cost basis of the project, the capital cost basis. So if there is a solar inverter that may be available and can be leveraged, that would really help in the net present value and internal rate of return calculation. On the other hand, if the equipment is very expensive, if we get to, let's say, $600 per kilowatt, our IRR diminishes. Similar story with installation cost. Obviously, the less it costs to install a connect a forklift, the better internal rate of return. Depreciable capital of the vehicle turned out not to be as important. This has to deal with the rather few hours of operation that the equipment does every year. So even if the forklift or the vehicle is more expensive, it doesn't impact the IRR as deeply. Same thing with cost of hydrogen. As we're not operating a lot of hours throughout the year, cost of hydrogen isn't an important factor. You can have expensive hydrogen and still have roughly the same business case. This parameter here is also fairly unimportant. Basically, any derating of the equipment for electricity production versus moving the forklift itself. Amount of fuel available per forklift is important. One thing to keep in mind is that this particular analysis is a factorial analysis. So at 2% depth of peak shaving, even if you have more fuel per forklift, so if you have 1.8 kilograms, it doesn't really buy you that much more. And lastly, this is the most detailed parameter that we analyze, looking at depth of peak shaving. There is an optimum. It's reasonably close to 2% in this case. Now, I mentioned that we analyzed 103 profiles. This chart is a bit of an eyesore, but it really summarizes the performance of all of those profiles. What we have in here on the x-axis is the demand, average kilowatts demanded for each of the profiles, starting from as little as 2 kilowatts and going all the way up to 1.5 megawatts. One thing to keep in mind is that this is a logarithmic scale in order to get the data to line up in a little neater fashion. Generally, we're looking at the best peak shave depth. Each profile is going to have a different optimal. So, for example, the profile that we just looked at had about a 1.5% was the optimal peak shaving. Some profiles may benefit from deeper peak shaving. The optimal performance may be at a deeper peak shave or shallower peak shave. So on the y-axis on the left here, and the red dots, red dashes in here, is the optimal peak shave. In green, we provide the corresponding internal rate of return for each of the peak shave depths. And as you can see, there is a pattern. The larger the building profile, the less peak shaving that is required for optimal performance. And also for the larger the profile, we're seeing a more robust and consistent positive internal rate of return for each of those installations. This particular analysis here shows in color a sensitivity for all of the profiles and all of the parameters, outlining in blue you have less favorable IRR, and in red you have more favorable IRR. And the things that we see here, again, we're seeing that throughout all the profiles, if we have a cheaper power electronics, we tend to get into the red numbers, which is actually higher internal rate of return. We're seeing that throughout all profiles, having a more favorable installation costs gives you a better return on investment. And again, we see the sensitivity where the larger the profile, the less we want to peak shave. The red occurs at a shallower depth. So it's nice that fuel cells have a positive internal rate of return for peak shaving, but what about the competition? We looked at other equipment that can serve this application, and we focused on gensets. So this is a combustion device either using natural gas or diesel. And these are typical numbers for such a device. Installation costs per kilowatt. This is the fuel usage, operating and maintenance. When we did analysis for this, we focused on diesel, and also since there is less uncertainty about how you would install a system, there is no inverters to consider. The fuel price is fairly narrow. We basically looked at only the sweeping of depth of shaving. So this is what the two charts, summary charts for diesel look like. Again, depth of peak shaving is in red, and internal rate of return is in green. There is less of a sensitivity to demand size, and also the total IRR tends to be a little bit less because you're attributing the total cost of the system to peak shaving, whereas if you have a fuel cell, that fuel cell would have been purchased for the purpose of moving equipment through moving material through a warehouse, and not primarily purchased for peak shaving. So the internal rate of return is a little bit penalized on diesel systems because you have to explicitly purchase equipment that is for peak shaving applications. In this slide, what we're seeing is it's a bit of an eyesore, but what we're seeing is a bunch of green arrows and red arrows. This represents the analysis differential between that building being served by an electric forklift or that building being served by a diesel peak shaver. If the IRR is greater for a diesel system than for a material for a forklift system, we show a red arrow. And if the IRR for forklift happens to be better than we generally what we're seeing typically for larger installations, you would find better performance with material handling equipment. And for smaller applications, we're seeing that diesels tend to outperform hydrogen equipment. So some of our findings, material handling equipment can be effective as peak shavers. I'm going to also just verbally say that we have done similar analysis for light-duty fuel cell vehicles. The numbers look similar, but that analysis hasn't been is not completely published, or rather, it hasn't really gone through its full paces before presenting to this audience. But in any case, material handling equipment can be effective for peak shaving. Larger buildings, the better. Refueling helps if the equipment can be refueled when it's empty. If there is a busy day and somebody can keep an eye out, or there is some sort of an alarm that says, hey, the fuel cell is almost empty and it can be refueled, that can help substantially on the business case in both net present value as well as IRR. The equipment, material handling equipment as peak shaving can compete with combustion equipment. It is the performance is highly subjective to the particular profile, to the time of use rate structure. So you really need to have a case-by-case analysis to confirm that you would have a good business case. And this analysis was performed for California. The time of use prices are rather high for California. Other places may be less favorable, but at least in California, we're seeing that this is a viable business case. With this, this is the end of my presentation. I believe Pete has been keeping track of any questions that may have come in, and the remainder of the time we'll take questions.
Okay, thanks, Mike. First of all, we apologize for not able to see the presentation initially. Just so you know, I share your pain. Mine didn't work either, but I had a cheat sheet so I could go right to the slides from my PowerPoint. But I think hopefully everybody had that corrected just by logging out and then logging back on. That's the typical way to do it. First question is, how would this change if there were low carbon fuel standard credits for hydrogen dispensing? Could you hazard a guess on that, Mike?
Yeah. So specifically for dispensing, I'm going to go to this slide here. So specifically for dispensing would impact the total cost of hydrogen. So for example, if your levelized cost of hydrogen is $8 with fuel credits, you might go down to $6. That wouldn't impact your business case very substantially. However, if there are incentives for a forklift, or if you are able to justify that the forklift is used in a stationary application, you're able to get some credit on the either in the installation or the power electronics. Those particular factors would indeed impact the business case in a positive manner. But the fuel specifically, we use so little fuel that even if it's cheap, that wouldn't really impact the business case.
All right. Okay, I've got a question for you, Mike. The diesel genset is dedicated to the peak shaving. If it was on a forklift and only used at peak times for a limited amount, as we showed in the fuel cell, how would you think that might affect the arrows?
That's a great question. I don't believe that. Well, I don't know that diesel genset forklifts are the same as electric forklifts. I would imagine that they're, and if there is somebody online that knows this better, but I would imagine that they're more of shaft power and gears that transfer the energy to the tires and to the operation of the forklift. I don't know that they are. That there's an electric bus on board that can be offloaded to the grid.
Right.
So I claim ignorance on that one, but I suspect that they probably are not compatible.
Okay, the next one is, have you looked at or included the value of potentially using material handling equipment to provide power during an outage, like emergency backup?
That critical loads the nodes fast enough to serve as a backup power. However, if you do have a forklift out of the fleet that happens to be sitting idle and it's plugged in, that may be able to for being able to handle a substantial portion of the loads, that would be a favorable business case scenario for peak shaving applications. But it will be a substantially different analysis.
Yeah. Okay, the next one is a more practical question about how would a customer know when to connect the fuel cell to the grid? How would they know that a peak has occurred?
Right. So I've looked at a number of facilities of this type, and always there is forklifts that are not being used 100% of the time. I've been in facilities during their busiest times, and there is always some equipment that is sitting idle. Now, if that idle time is spent while the forklift is, there is a cable that's connected for on one or two of the forklift fleets, that would serve that function.
So, how about this one? Typically, moving materials in diurnal periods or during peak periods of peak demand. In other words, in the middle of the day, often forklifts are at their peak requirement. They can't just pull up and start to specify the peak shaving. Have you got any data on that to support or refute that?
I believe we do, but we've considered this. Again, I'll wave my hands and say that whenever I have seen equipment, I've never seen all forklifts operating at the same time. But again, that's an important consideration of engineering, detailed engineering assessment for any application to look at, well, how many forklifts are actually idle at any given time? Is that sufficient capacity to provide meaningful peak shaving, and look for feasibility there? So, for example, one of the facilities in here is a package distribution facility, and typically they do a lot of their work either in the small hours of the morning or late in the evenings when packages are coming in and coming out. And as a matter of fact, that does not coincide with their diurnal peak for electricity demand. So some judgments may need to be exercised, as well as detailed engineering assessment to follow that to make sure that it is actually feasible to have sufficient forklifts.
Right. I suppose if you had to buy a couple more forklifts, just because you're taking two offline and using them for peak hour shaving, you'd see a different economic situation.
Yeah. Well, another thing to consider is that frequently, as with battery forklifts, you would have spares that are there for for spares, and for the equipment that's on a forklift, it typically has hydrogen storage, it has cooling, it has the full capability of producing power, even if it's not connected to a forklift. There is actually a benefit of operating a spare piece of equipment once in a while. It reconditions the stack and makes sure that it doesn't dry out and degenerate. So another way to look at it is that you would connect spares that are sitting idle and have zero function other than being standby equipment. And in this type of operation, they would incur very few hours, and it would actually expand their shelf time by operating them once in a while for peak shaving applications.
Okay, fair enough. So any other questions before we sign off here? I don't see any on my question block. So I'd like to thank everyone that listened in, and I'd like to thank Mike very much for a great presentation and very insightful information and analysis. So thanks, everybody.
Hey, thanks to all of our speakers. That's going to conclude our webinar today. If we didn't get to your questions, please feel free to email the presenter directly, and they will try to respond to you in a timely manner. Again, I'd like to thank you for joining in and remind you that the webinar and slides will be available online at the website below there, hydrogenandfuelcells.energy.gov. The webinar and slides will be available in about 10 days. Also, I encourage everyone to sign up for our monthly newsletter, which includes upcoming webinars. You can sign up for that on the website shown below as well. Have a great week, everyone. Thanks for joining.